So streaming is on right now, and it's going to take a few seconds for people to actually see it on the YouTube side. Oh, okay, it does. Okay, I did not know that. I suppose it's easy to check too because I can always just check my YouTube window. So the YouTube window is up, it is streaming. Excellent. So now we are ready to go. All right. So, do you guys want me to go over the answer of the CNF assignment, or are you guys just going like, okay, I think I have enough of this, Boolean algebra already, and just kind of move on? I'm okay either way, so just let me know. All right, sure, we can go ahead and do that. So just like those infomercials, I have these dishes already prepared ahead of time. So you won't show me, you won't see me fumbling, with my own Boolean algebra derivation. So this is all done already. And you can see that, I had to check multiple times because sometimes I get to the end, it's like, nope, the truth tables do not match up. And it's easy to make mistakes like that, okay? And, I made those mistakes too. That's why I had, like 3 intermediate, checkpoints here, here, and also here to see if my derivation is correct or not. Because sometimes I just copy it wrong, and other times I apply the rules incorrectly, just accidentally. I understand the rules, but sometimes I can do it kind of, incorrectly. All right, so let's go ahead and look at the proof, step by step. So this way, if you have any questions about the application of Boolean algebra rules, you can go ahead and ask me. But if you want to ask, but how do you when to use which rule? That is a much more difficult question to answer. I just kind of go like, look at this, maybe we should try that, and so on. There are certain general directions, so I can tell you about the general directions, but when it comes to certain choices, it's just a hunch. Okay, so it's just like your algebra class when you're solving, 2 algebra expressions and try to prove one is really the same as the other one. A lot of that is kind of experience, and some of that is practice. And there are some general rules of thumb, um, and that's about all I can say, unless some of you have some further insight into this. All right, so getting into the current assignment, the CNF. Okay, I've had lots of trouble with how to distribute. So distribution, you just have to kind of understand the pattern, right? That's the thing you have to do, is to really understand the pattern, and understand when you can apply, which pattern. Now, understanding which pattern is applicable is a big deal, because that means you know what options are available to you at any point of this derivation here. All right, so I am just going to re-point out the distribution rules. So there are 2 distributions in Boolean algebra. So in Boolean algebra, one distribution is A or B and C is really the same thing as A and C, or A and B and C. There we go, B and C, like that. And in this notation, I've been using this notation for a while already. I hope you guys are getting used to it. What looks like multiplication is conjunction. What looks like addition is actually disjunction. So that means A or B and C is really the same thing as A and C or B and C. So this one looks just like the usual distribution that you already understand in algebra. The next one is applicable in Boolean algebra, but not so much in normal math algebra. So it's A and B or C, and that can be seen as A or C and B or C. So this is the one that takes a little bit of getting used to, but once you understand the pattern, okay, it's just like, oh, okay, so it's kind of like the first one, except in this case, I'm also using the implicit priority of conjunction is being higher compared to the priority of disjunction. So if you want me to be a little bit more clear, I can put in extra parentheses like that. So I think that's the one that makes it, that's a little bit awkward for most people, coming from just regular algebra, is this also works in Boolean algebra. Now, if somebody is, I'm not saying that anyone is, okay, but someone is looking at this and go like, but this looks really weird. Are you really sure this works? Well, what would be the answer? If somebody was to ask you, okay, and say the second form of distribution, it looks kind of awkward, it definitely does not work in normal algebra, how do we know this works in Boolean algebra? What would be your answer? How would you approach that question? So that's the first thing I want you guys to think about, okay? Because you already have all the tools to answer that question. The question is, do you know how to do it? So I'm gonna let you guys try to figure that one out first, and once you have that one figured out, we'll kind of go back here and answer these questions. All right, not seeing any answers. Come on, you guys can answer that question. I mean, by now you probably should be kind of tired of me, mentioning those two words again. Exactly, truth table. You can have a truth table for 3 independent Boolean variables, A, B, and C, and just make sure that the left-hand side of this equality evaluates to exactly the same value as the right-hand side for all 8 rows. And if that is the case, then we know the two expressions are truly equivalent. And that's it. Okay, you cannot do this with normal algebra. Okay, with normal algebra, because it's impossible to exhaustively test the expressions, because the set of integers is infinite. On the other hand, the set of Boolean value is not only limited, it is very limited, right? Because we only got 2 values, true and false. So there are very convenient techniques that can work in Boolean algebra that simply does not work with normal algebra. So that's one tool that you guys can kind of keep in mind as you try to solve these problems. Alright, so we still have Nathan typing, so I'm going to wait a little bit before we proceed with today's first thing, which is the CNF assignment. Because once we are done with the CNF assignment, then we're going to move on to the next assignment, which some of you have already predicted, and that has to do with proving whether an expression is a theorem or not. Alright, well, it looks like Nathan may not have something to share with the class, because I am not seeing anything in the text channel. Alright, well, that's fine. Alright, so getting to... Oh, okay, it went to off topic, I guess. Okay, I'm not going to get to off topic. That's a reason. There's a reason why that channel is called off topic, so I'm not going to go there. Alright, first line to the second line, that's just the definition of implication. And then from the second line to the third line, it is also the definition of implication. The third line to the fourth line is, I'm just looking at De Morgan's law. There we go. So this is De Morgan's law and simplification applied at the same time. And the De Morgan's law is applied to right here. So this part is where the De Morgan's law was applied, and it became P and not R. And you can see right here I'm using the implicit priority of operators already, so this way I don't have to use a lot of parentheses. The problem with parentheses, the nice thing about parentheses is it's very clear, okay, how operators are grouped. The downside is, it can be very confusing. I mean, I have to count parentheses and make sure that they are all right. And that's one problem with the prefix notation. I'll show you guys what I mean by that in just a little bit. Alright, so then this becomes from the fourth line to the fifth line. That is the application of De Morgan's law again. And this time it has to do with this negated or anytime you have a negated or a negated and, you can apply De Morgan's law. So when I apply De Morgan's law, I'm simply distributing this negation into the components. Okay, this is the one. This is one component, and this is the this is the other component. So it became like this. So the or becomes an and. That's the result of De Morgan's law. And then from the 5th line to the 6th line, let me see. That's also De Morgan's law, right? So I am applying this negation of the conjunction here, and also this negation of this conjunction here, and that's basically 2 applications of De Morgan's law, but they are not in steps, right? They're parallel. So now we end up with not P or R and not Q or S, and then we have a or, outside of the and, because and has to be performed first. It has a higher operator priority. And then we have a or, and then the other side is just R and not T. Alright, so this is where the distribution stuff gets a little bit weird, because you cannot do that in normal arithmetics. So this distribution is to take this is using this pattern here, right? Because if you look at A as not P or R, and you look at B as not Q or S, and then you look at C as R and not T, not R and not T, then we can use this distribution, and then we just end up with this line over here. So I think that probably is the most difficult part, or the most tricky part of Boolean algebra, is there are certain things you can do with Boolean algebra that you cannot do with normal algebra. Alright, so Nathan printed something here. General steps, convert implication. Yep, that's the easy one, because in CNF there's no implication, there's no imply. And then simplify negations using De Morgan's law, which means you're basically distributing the negation all the way in until they are applied to individual variables. Distribute or operations. Okay, so A or B and C is A or B and B A or C. Yep, so that works too. But in this specific case, it is distributing the other way. Oh, no, it's the same. Okay, so never mind, it's the same. It's just that the way Nathan writes it is the term being distributed is on the other side. But that's okay, because disjunction is commutative, which means ordering is not matter. Okay, whether we say this is AB plus C or C plus AB, doesn't make any difference. All right, cool. So now what do we do? Well, we end up with P, not P or R and not T. So it's close to being a CNF, but not quite. Now, but the nice thing is, if I turn this side into a CNF, oh, wrong side. If I turn this side into a CNF, come on, and then I turn the other side also into a CNF, those two CNFs can be concatenated, because when you concatenate two CNFs using a conjunction, the resulting thing, which is also a conjunction, is also guaranteed to be a CNF. So this is divide and conquer. Okay, this is divide and conquer. So now when you look at this pattern here, okay, it has a pattern that looks like this. But this time we are distributing oh yes, so it definitely has the same pattern as this. So this time what you do is you look at P or not P or R. Okay, look at these two, look at this junction here as C, and then you look at R as A, and then you look at not T as B. So now we apply the same distribution, okay, which is the one that Nathan just quoted. Okay, it's this one here. So once we apply that, this side, so when this side here, okay, I need to clearly indicate which one. So this side becomes this thing here, and then the other side obviously becomes the other side. And then we can apply some simplification. the simplification can be done because when you have a gigantic conjunction of disjunctions, if two disjunctions have almost exactly the same term, except one is more general, which means it has more rows being true than the other one, then you can take out the more general term because when in the disjunction it's only the restrictive term that actually matters. So that's why not P or R or not T is simplified out. And then here there's another simplification. Not P or R is just not P or R. Okay, so that's how we can do two simplifications, and basically the bottom line is this entire thing over here simplifies to just not P or R. Now the other side, there's not much you can do about simplifying. I mean, that's there's nothing you can do. So this becomes the answer, and yes, I did check it. Okay, so this is correct. All right, so let me take a look at what Nathan has posted. All right, so there's a truth table, and he is showing whether the not T is there or not does not make any difference when you are ANDing those two terms. Very nice. Okay, very nice, Nathan. That is very good as a visual way to look at it. Now, the way you can create a truth table is you can do it by hand, right? You can just kind of evaluate if P is false and Q is true and then R is false and blah blah blah. You can just do it by hand. The way that I did it, and I'm going to say ahead of time that I will not be sharing this spreadsheet, is like this. Okay, let me see right there. All right, so the way that I did it, okay, because I am, I wouldn't say clumsy, but I do make mistakes, just silly mistakes here and there. So along the way, I made mistakes. So I have to make sure that everything boils down to the same thing. So this is basically one of the stages of the expression, and you can see this is an infix notation because in the spreadsheet they do not have operators for or and not. So everything are formulae. And as a formula, okay, it is an application of a function. And here you can see how the parentheses are just kind of stacking up. I mean, it's not like they're not trackable, but it's really a hassle to have to count parentheses. So this is the way I did it. I mean, I just use a spreadsheet and then enter the expressions and just check, make sure that for every single row, they have the same value. Obviously, column HI are basically snafus. I made a mistake, and they don't match up. So I know that I have made a mistake in my derivation. So these are tools that you can use, okay, in order to kind of check your answers and so on and so forth. Are there any questions? Oh, Philip is typing something, so I'm gonna pause here and see if there are any questions I can answer. All right, maybe not. All right, so I'm not gonna wait. So that's it, right? So I'm gonna take row right now. I know it's a little bit early, but I hope everybody is here already, so I can go ahead and take row. All right, so the question is, what is the word for row taking? And the word is Harry, from Dirty Harry with Clint Eastwood. Let me paste it into the text channel, and then I'll release it. I'll give you guys 15 minutes to answer that question. There we go. All right, so it's 20 right now, so I'll give you guys up to like 35. That should be plenty of time. There we go. All right, so let's go ahead and take row first. And if anyone is thinking, why do you use Harry as as a passcode for today. That's because eventually, because I have to talk about your next assignment first, but eventually we're going to go back to discrete probability. Okay, and one of the sentences, one of the quotable quotes of Dirty Harry is, "Do you feel lucky?" Right? No, no, he doesn't quite say it that way. It's hard to imitate Clint Eastwood. Yeah, but that was the reason. Do you feel lucky? Because we are talking about probabilities. So every time anyone goes by a lotto ticket, that person really should think of Clint Eastwood as Dirty Harry saying that phrase. Eat some cotton. Yeah, Clint Eastwood became a mayor, right? Became a mayor of a town in California. I cannot even remember which town. Was it next to Monterey Bay? Carmel. Oh, yep, Carmel by the Sea. That's it. And I think that's interesting, to say the least. Anywho, I think we are done with road taking right now. Um, so I'll give you a new assignment. Let me close the road taking thing because I won't need that anymore. Alright, so your new assignment, let me show you to that. It has not been released yet, okay? Because I cannot release the new assignment because it contains the answer to your to the one that was just due. So here is resolution and proof by contradiction. You have a week to work on this, so I suggest that you start early because this one is not any easier than the previous one. If anything, it's a little bit more complex than the previous one, but you can reapply a lot of the techniques of the previous one. Alright, so I'm just using the shorthand because I got really tired of having to type all the special symbols in LaTeX. So the solution is this, which is what you saw in my notes for today. Okay, so it's basically the same final notation for today's for the assignment that was due today. So that's exactly the same thing, but this time I want you to prove whether another statement is a theorem or not. In other words, I want to see if this is implied by that. And I also want you to see if this is implied by that. So you're going to have to use resolution and also proof by contradiction to answer these questions. So the bottom part of the assignment text also indicates the priority from high to low of the operators. Negation has the highest priority, which means it applies to whatever is immediately to its right hand side. And then we have conjunction, and then we have disjunction, and then we have implication. Now typically when we have disjunction and implication, I would use parentheses to make it very clear which one should be applied first. But in the absence of parentheses, we have these implied priority of operators. So just to make things more clear, not PQ is really the same thing as negating P first and Q. So the Q is not negated, is not a part of the negation. And then PQ implies R is the same thing as P and Q. The whole thing implies R. And then P not Q plus not RS is the same thing as P and not Q. And then take the entire conjunction and OR that with the conjunction between not R and S. Okay, so I just want to make sure that everybody understand the priority, and so that you guys, when you use these notations in your proof, then we won't get into problems, right? I won't be looking at the derivation and go like, no, that does not apply, and then later on somebody comes back and say, but I thought, disjunction has a higher priority, or at least the same priority as a conjunction. So I just want to make sure that everything is clear for this assignment. Are there any questions about the new assignment? And if not, I can assign it right now. In fact, it's already assigned. It's just that I have not published. So there we go. So I'm going to publish it. You will turn it in latest by April 4th for that to count. So save and publish. There we go. All right. So any other questions about CNF, resolution, proof by contradiction before we get back to discrete probability? Because I did promise you that we're going to get into those awful notations, the omega notation and also the big U notation, and those are recursive subroutines. So we are going to have to get into that. But before we do, I would answer questions related to CNFs and resolution and proof by contradiction first. All right, no questions. Okay, all right. So once again, I would strongly advise you guys to learn how to use a spreadsheet or a C program. I mean, CISP430 is a co-requisite of this class, which means all of you should have taken CISP400 already, which means you should have taken CISP360 already, which means you should have known how to use a loop or a nested loop, to basically come up with all of these, test patterns, and then translate the Boolean expressions, and then you just kind of keep track of whether two expressions are the same for all the values of whatever variables you're using. So, so you have a lot of tools at your disposal to kind of work on these things. All right. All right, so let's go back to our regularly scheduled program. We are returning to our regularly scheduled program. And we're going to go back to counting. Yeah, so I know the title of the module is quite deceiving because all it says is counting. It's like what can we possibly talk about when it's just counting? Well, as it turns out, it's a little bit more than that, right? All right, so we are, let's see. So we are done with this notation here. Basically it is just a notation, P and M, P of NM, or P of, choosing M from N is N factorial divided by the factorial of N minus M. So we definitely talked about that last time. We also talked about ordering. No, actually I do not think so. I don't think we talked about ordering. So this is going to be our new topic here. All right, so we talk about lotto, right? So if ordering is important, in other words, if the lotto ticket of 1, 2, 3, 4, 5 is considered different or unique from the lotto ticket 5, 4, 3, 2, 1, then we're going to be overcounting the number of possible lotto tickets, because lotto tickets are not, ordering is not important when you choose the 5 lucky numbers on a lotto ticket. So the question is, okay, so given that is the case, okay, given ordering is not important, how do we count the number of unique lotto tickets? Well, there are a few ways to do it. The first way is you still count permutations first, okay? So you're still considering 1, 2, 3, 4, 5 to be different from 5, 4, 3, 2, 1, which is different from 1, 2, 3, 5, 4, which is different from 5, 4, 1, 2, 3, and so on, right? So now the question is, if I give you just 5 numbers, okay, so the 5 numbers that are given to you are 1, 2, 3, 4, 5. The question is, how many ways can you rearrange these 5 numbers? That becomes the next question, because if we know that, we can just say, oh, given any 5 actual numbers, there are this many permutations, and we just have to count all of these permutations as one single combination. So a simple division would have taken care of the case of, let's not count all the duplicates, because we know how many duplicates are to one particular combination. All right, so what is the answer to that question? If I give you 5 numbers, 5 unique numbers, how many different ways can I come up with the sequences? So the other way to look at this is to say, okay, I give you 5 unique marbles, right? And I put it in a bag, and I ask you, okay, you can draw 1 marble out of the bag at a time, and it is without replacement. So once you take a marble out, you don't put it back. So the question is, how many ways can you choose the first marble? 5, right? And how many ways can you choose the second marble? 4, right? Because the first marble, once it's out, you cannot choose that marble again. So the second marble in the sequence, you only got 4 choices. And then the third one, you only got 3 choices. The fourth one, you only got 2 choices. And then the last one, you don't have a choice. Okay, there's only 1 marble left in the bag, and that's it, right? You don't have a choice. So you guys are all, so Elijah and Chris are both correct. It is 5 factorial, which is 120. So there are 120 permutations for every combination when we want to choose 5 items out of, in this case, 69. So the end result is, if you're interested in the number of combination, which is the notation, the notation of choosing, combinations can be simplified like this, which is kind of awkward, right? Because it's 2 parentheses and then have the original number of items, on top, and then the number of items that you're choosing, the number of items that you want to be chosen at the bottom. So this is n choose m, okay, which is also the combination of n choosing m. And that turns out to be just n divided by n minus m factorial, n factorial divided by n minus m factorial, which is p of nm. But then we also have an extra term of m factorial, because that accounts for the number of permutations when you have m items chosen, and you go like, okay, all of those are considered duplicates, so we want to divide the number of permutations by m factorial, so this way we are left with the number of combinations. Yep. All right, so are there any questions about the CNM, the number of combinations, and how we compute the number of combinations by dividing the number of permutations by the number of permutations once you have chosen 5 unique things from the original collection? Alright, so I'm going to wait a little bit because I can see Nathan is typing, so we'll go ahead and wait. Oh, okay, alright, cool. Alright, so now we have the 2 important notations. One is computing the number of permutations, and the other one is computing the number of combinations. Alright, so now we are, so I'm not really sure whether you guys want to get into the thick of this, which is the recursive definition of generating the set of outcomes for permutation, and then generating the set of outcomes for combination. So let's not go there yet. Okay, let's go ahead and solve a problem first. Okay, so we're trying to apply what we have learned and see, what can we use, these notations and concepts for. So before we go there, I'm going to go to the side here because I cannot do that. I cannot show you guys. Well, I suppose the enrollment is not a FERPA issue, but still, I'm not gonna risk it. So I'm looking at the enrollment for this class right now because, as an example, I want to. Oh, okay. Because I want to use the birthday problem as an example. So I am getting the enrollment of this class. So we have 29 right now. Okay, so we have 29 people in this class. So my question is, what are the chances that at least 2 people in this class share a birthday? That's the question. That's it. Okay, what are the chances that there are at least 2 people in this class sharing the same birth date? So we are not counting the year, we're only counting the date. And for the purposes of this discussion, we can assume that a year has 365 days. So we're not going to deal with the uh, um, leap year thing. All right, so Chris says more than 50%. The question now is, how do we compute that, right? How do we compute the chances? Now, the chances is not it's not intuitive. Okay, I can tell you that it's not intuitive. So the question is, how do we utilize what we have learned here to answer that question? So what I'm about to do is to show you, the reasoning. Okay, how do we reason this out? All right. Not quite, okay? Because we can end up with I want to consider the possibility of all 29 students of this class sharing exactly the same birth date, right? That's possible, okay? It's not likely, but it is possible, right? So I can have 3 people, having this birth date, 2 people having that birth date, and then the rest all have different birth dates. So I want to consider all of those, okay? In other words, my real question is, what are the chances that we do not have unique birth dates for everybody in this class? That's basically what the question is asking. All right, so now induction is an interesting way to look at it. It's a very good way to think about problems. Okay, so thank you, Chris, for proposing that. Okay. All right, so let's use that. Okay, I'm gonna run with that idea of using quote unquote induction, even though it is not exactly induction, but it's a way of looking at things. It's a way of solving problems by not so much example, but trying to extend a problem that has a known solution and just go like, okay, what if the problem size is just one more? And what do we have to do? So that's kind of what we're going with at this point. All right, so we're going to go with restating the problem. Okay, so I'm going to type it here. So the original problem is, what are the chances that at least 2 people in a class of 29 share the same birth date? Okay, so that was the original question. But the original question can be restated in a way that is easier to solve. So the other way to say this is, what are the chances that birth dates of people in a class of 29 are not unique? That is now the question. So with this question, one way to look at this is to say, oh, okay, so if I can figure out what are the chances that everybody has a different birth date, then I just have, I can just say, okay, it's 1 minus that, because it is the complement that we want to answer in this question. So if we figure out the other one, so we can say, okay, first figure out the chances that all 29 people in a class have different birth dates. All right, so now the question is, all right, so let's try to figure this one out first, because once we figure out the chances that all 29 people in this class have different birth dates, then we can just say, oh, 1 minus that is going to be the answer that I'm looking for, because I'm looking for the chances that at least 2 people share the same birth date. So now, how do we answer this problem, this question here, which is the simplified question? This one is kind of simplified. All right, so how do we approach this, right? So the one thing you can do is basically to say, in order for this to happen, let's put all the dates in a year, okay? January 1st, January 2nd, January 3rd, all the way down to December. I have to do the knuckle trick to find out how many days there are in December. So December has 31 days. So if I just write down, okay, every possible date in a year on a little slip of paper, okay, there are 365 of those, right? Going from January 1st to December 31st. And I put it into a bag, okay, or tray, whatever you want to use, as a container. And I'm just asking each person in this class to go to that bag and pick one, piece of paper out of that bag. And that will basically tell me how many total ways, okay, how many ways can we choose 29 dates out of a bag of 365. So now we know we're dealing with either a permutation or a combination problem, okay? But now the question is it combination or is it permutation? So we want to think about this a little bit, okay? Just kind of imagine in your head, we have a line of people, okay? So I'm asking all 29 people to form a line using their student ID for sorting purposes, right? And I ask, each person to, go to a bag, pick one item out of the bag, and move on. So the question is ordering important in this case? So to understand that problem, you kind of have you can simplify the problem and just say that what if there are only two people in this class? Okay, so for whatever purposes we want to use here, we'll say okay, we got person A and person B in this class. So the question is okay, and we'll only consider two possible dates of the year. Okay, so we are only considering April 1st. And also, okay, find another funny day to choose. Choose another funny day. What would be a good funny day to choose? Pi Day. Okay, Pi is good too. Yep. So we have March 14th and April 1st. Okay. So does it matter? Is it considered different if person A has Pi Day and then person B has April Fool's Day? Or and versus the other way around, person A has April Fool's Day and person B has Pi Day. Are they considered two distinct cases? That becomes the question that we need to answer. Yep, so Elijah is correct. Okay, indeed, they should be considered two distinct cases, and Philip is correct as well. So now we know we're dealing with permutation because, if we just simplify the whole thing down to, okay, there are only 2 days in a year and there are only two people in this class, we still want to consider the two ways of assigning dates in the year to those two people to be different. So we're dealing with permutation. All right, so let's write that down. Okay, ordering is important. And then the other thing we have already noticed is it is without replacement. Because once you have chosen a date out of the bag, you don't put it back in because we want everybody to have a different birth date. Okay, because we're counting how many ways can we assign 29 unique dates to people in the class. All right, so having these two information is super useful because now we can say, oh, okay, so we are looking at choosing from 365 possible dates in a year. There are 29 people. All right, so we know this number is important. The question is, what is it representing? We know this number has to do with without replacement. We know this number has to do with ordering is important. And we know this number has to do with there are 365 possible things. In other words, that is the cardinality of the set of outcomes for the first trial. And there are 29 trials because there are 29 people, each one going to the bag and pick up one item. But the question is, what is this representing? Well, what this is representing is the number of ways to assign 29 unique birth dates to people in a class. Okay? All right. But that by itself is not a probability, right? Because this is a huge number. So it is not by any means a probability, because when we're talking about the probability, it has to be a value between 0 and 1. And most people look at probability in percentage, but a percent is nothing more than just a value between 0 and 1 multiplied by 100%. Okay, it's really just it's a colloquial way to look at proportions, because most people do not like decimal points. I'm gonna guess that is why we like to use percentages, but that's basically what it is. And we need to know the total number of ways to assign 29 birthdays to get the cardinality of all the possible outcomes. Okay, so this is not really all the possible outcomes. This is all the possible this is the cardinality of the outcomes that we are quote unquote interested in. But it is not representing how many ways we can have birth dates actually assigned to people. So let's deal with that problem. Okay, so now the question is, without any restriction, how many ways can 29 people have their birth dates? That becomes the next question, right? If I don't say any restriction, okay, at least 2 people must have the same birth date, or everybody must have unique birthdays or whatnot. Okay, if I don't say any restriction, you have 29 people. I want to find out how many ways can we have birth dates assigned to these people with no restrictions whatsoever. So the first person comes up to the line, and I say, okay, what's your birth date? Oh, it's March 1st. Okay, fine. Second person, come up. What is your birth date? Whatever, right? So how many ways can we assign birth dates to 29 people in a class when there are no restrictions? So I want you guys to think about it and try to answer that question. So Nathan is correct. The total number of ways to assign 29 birth dates without restrictions. Okay, so the key here is without restrictions. So that is equivalent to someone walking up the line, the head of the line, and that person can choose any one of the 365 days. The next person coming up, guess what? That person can also choose from any one of the 365 dates, and so on. So all 29 people can choose any one of the 365 dates in a year. So now the question is, well, if there are no restrictions, how many ways can we do that? In other words, we are trying to figure out, with this kind of experiment, what is the cardinality of our omega. It's quite a bit more than that. Alright, so we are looking at the omega, or the set of all possible outcomes without restrictions. So once again, it's best to kind of go all the way down to 1 person in the class. Okay, so if we have only 1 person in this class, and when I'm asking how many possible ways can we assign a birth date to that 1 single person, that's a silly question. It's 365. Okay, we got that. What if we have 2 people in this class and there are no restrictions, right? So now you go like, okay, the first person can take any of the 365 days, and guess what? The second person can also choose from any one of the 365 days, because whatever date the first person has chosen, it can be chosen again by the second person. So that means we are looking at 365 raised to the power of 29, because there are 29 people in the class. Thank you, Chris. Alright, so I am going to put the answer here. So this omega, or the cardinality of this omega, is 365 raised to the power of 29. So there we go. And that's a very interesting number that Chris has posted here, because it is an actual number is not in scientific notation, because a lot of times, if you just punch this, equation, 365 raised to the power of 29, you can get a value. Okay, that's an approximation in scientific notation. And the reason why that is the case is because most computers and spreadsheets and scripting languages and C and C++, with a value this big, they're going to use a double precision floating point number. And if you took CISP440 from me, you should still remember that with a double precision floating point number, the mantissa, which controls the precision of the number, only has 52 bits. So that means it cannot resolve values. There are only 2 to the power of 52 values that are distinct when it comes to the mantissa. Okay, they can be different in terms of the sign or the exponent of 2, but when it comes to the precision part, there are only 2 to the power of 52. 365 raised to the power of 29 is exceeding that, okay, by a long shot. So the fact that Chris was able to quote the number that ends with a digit of 5, because remember, 5 raised to any power other than 0, or something that's negative, 5 raised to any integer that is greater than 0, okay, there we go, would end up with a value that also has 5 as the least significant digit. And the number that Chris posted in the text channel ends with a 5. So I'm suspecting it is an exact number. So there you go. Okay, so but your calculator still has an internal representation limitation, and I would basically say that it's not going to be able to represent the actual value of 365 raised to the power of 29. Not that it's important to us, okay? We just need to know, the chances, so we're going to do some division using this. So it's not super duper important to understand, are we looking at the exact value or are we looking at an approximation of that value? It's not really super duper important. I just wanted to note that what Chris has posted is an exact number, and it's not easy to get it to, but it does. I'm not sure. That's not from a calculator, right? Because when you solve it, it is using probably Mathematica or some other web-based engine to do the math. If you put it onto your TI calculator, it's unlikely. Okay, I haven't tried that, but it's unlikely that you're going to get 365. You're not going to get the exact value. All right. Oh, okay, I see. So you must have a calculator program that has variable precision. You basically can make an integer as large as you want. There's no inherent limitation of digits. I think when Professor Fox was still before he retired, that's one of the assignments that he likes to give, is for people to make it. Are those called elastic arrays? And then he would have people to implement multiplication and division, multiplication and addition with integers that have no inherent limitation of precision. So okay, so I just got sidetracked. Sorry. All right, so the probability that we are looking at, okay, I'm just going to use PR to represent the probability, is now a fraction. So the fraction has a numerator that is p, the number of permutations of 365 choosing 29, and it has a denominator that is 365 raised to the power of 29. So this is the probability, but what probability are we talking about? We are not really talking about the probability that we originally wanted to find. This is the probability of 29 people, 29 people in a class all having unique birth dates. There we go. But that wasn't the original question, right? So the answer, the answer to our original problem is going to be 1 minus that. So it's the probability of 29 people in the class and not all having unique birth dates. So that means at least 2 people share a particular birth dates. Okay, because I just put in a negation in front of the qualifier. There you go. So now the question is, what exactly is that amount? I mean, you guys can punch in the equation, the expression, and find the answer. And the answer is surprising. Okay, because most people think, well, maybe we are looking at 1/10 because 29 is kind of 1/10 of 365. And as it turns out, the probability of at least 2 people sharing the same birth dates, according to Chris, is 68%. It's more than half. So I think most people do not understand that there's a really good chance it's more than half that in this class, 2 people, at least 2 people share the same birthday. It's just counterintuitive. And this number also scales up in a very strange way. So if you look at a class of 30, a class of 31, class of 32, it actually increases pretty quickly. So if you have a class of, let's say, 60 people, which is my CISP440, that chance goes all the way up. It's like it is very unlikely that amongst 60 students in my CISP440 class that they all have unique birth dates. There you go, nice. So Chris has a plot. So at 60, at the class of 60, number of people being 60, you can see the probability of at least a pair. Okay, basically having at least one case of non-unique birthdays is I'm just guesstimating here. That looks like a 99, 98%. Yeah, it's highly unlikely that my CISP440 class do not have 2 people sharing the same birth dates. So there we go. At 100%, at 100 people, which is only less than 1/3 of all the days in a year, right? Because we have 365 days in a year, and 100 is less than 1/3 of that amount. But if you want to count the number of the probability of all 100 people having a unique birth dates, it is less than, I'm just counting the zeros here, so it's going to be less than 0.00003 of a percent. Okay, so 1% is 100. So just add 2 more zeros, to the zeros in that sequence. If you don't want to use a percentage. So it is counterintuitive. It is very counterintuitive. But intuition simply means that sometimes for people who do not understand the math, who have not been exposed to statistics or discrete probability and whatnot, so when they use what quote unquote intuitive ways of looking at something, the opinion formed because of that can be very different from what it really is. So I'm just gonna leave it at that. Okay, in my head I have a bunch of politically incorrect statements already prepared, but I have a little gatekeeper saying, no, you're not gonna say that, so I'm not gonna say it. So Chandra has proposed that we type in our birth dates into Discord. Well, if people want to participate, they can go ahead and go to the off-topic, channel. But I want to emphasize it is not going to be mandatory. All right, so this is an application. Okay, we have just looked at one application of studying probability, discrete probability, using combinations, permutations, and power. Okay, just exponent. The other application we have done already is to look at lotto tickets, right? So we look at lotto tickets and we ask, okay, what are the chances that you can get the jackpot if you were to just buy one single ticket? What would be the chance? Well, as it turns out, it's close to 300 million to 1, which is a pretty low chance. I mean, if you think about it, the population of the United States is 300 million-ish. Okay, it's a little bit more than 300, but we'll just call that 300 million. And if you think about the number of people who die from bee stings a year in the United States alone, I'm gonna say at least in the 10s. Okay, yeah. So the chances of being dying from a bee sting is actually higher than winning the jackpot of lotto. Oh, thank you, Chris. Yeah, you can. That's interesting. 62 people in the United States die from bee stings a year, and the number of people who die from sharks, okay, shark bites and whatnot, is actually lower. So when people say, oh, I'm not going to get into the water because the sharks can kill me, well, the chances of getting bees killing someone is actually higher. And the chances of dying from a car accident driving to the beach is also probably higher than getting killed by a shark. Yep. Oh, okay. Fun stuff, Chris. Good. All right. So now I'm looking at the time. We got about 18 minutes left. All right. So what we'll do now, okay, because now we got all the fun stuff out of the way, we can get back to the boring stuff. You guys go like, oh no, not that boring stuff again. Yes, we are going to get to the boring stuff. So we want to not just do the counting, because sometimes it is actually useful to find out what are the possibilities, what is my set of possible outcomes. Okay, now why would you care about the actual possible outcomes when we already have the tools to compute probability? So I'm gonna let you guys think about it a little bit. I may not be able to get to this, but I really want you guys to think about why sometimes we actually care about the actual outcomes and not so much just the number, not just the probability, because we want to know exactly what is in the set of the possible outcomes. What is that important? I mean, what kind of application would care about the actual outcomes? Alright, so for coding, you want to make sure everything runs. So that means, when you want to do an exhaustive search or exhaustive test for a particular program, you need to come up with all the possible cases, right? Every single possible case that a program is supposed to handle. If you really want to do it that way, that's one way to make sure that your program does work for all possible cases. So you need to find the actual set of possible outcomes. So very good. So Elijah has a very good point there. Okay, so that's one. What about other applications where you really care about the set of possible outcomes and not just the probability of something? Think back in time. Think Alan Turing. And if you ask who's Alan Turing, then I would just go, well, you need to watch The Imitation Game, as a movie, which is based on a historical figure that relates to us. And so by now, cryptography, exactly. So in other words, how do we rule out certain cases, right? How do we rule out this cannot possibly be the encryption key, this cannot be the encryption key, this cannot be the encryption key, because as Sherlock Holmes, okay, he may not be the first person, or I should say the novel may not be the first source that quoted, once you remove all the other possibilities, whatever is left, it's got to be it, right? So as it turns out, there are some hacking tools, that work just like that. Okay, they basically rule out impossible keys that cannot be the actual encryption key. So when you rule out all the ones that cannot be, whatever one is left, it's got to be the one, right? So there are cases where you want to generate, all of these possibilities, and then you just kind of cut them down, using certain techniques, using, and rule out, certain ones, so that this way, you can gradually get to the one that you want to get to. Um, and if you are not convinced about, applications where you want to find the actual possible outcomes, initially, and you just kind of rule out things as you go, I would encourage you to look into this. Okay, it's called, oh, what is the name of that game? It's gosh, I used to do that. Yeah, it is a brute force attack, but there are brute force attack where you can design the test very carefully, so this way it doesn't take nearly that long to cut down to one single choice left. And I'm trying to figure out the name of a board game that does do this. Mastermind, that's it. Okay, so Mastermind as a board game. Okay, I'm gonna go to the Wikipedia page here. It's one of those games. It's a fun game. It's a fun game, and there are certain variants to it too. Okay, so Nathan, I'm glad you have been exposed to a game like this. You can actually download an app and play that game. Probably remotely with a person or just against the computer, or you can be the one hiding the pattern and have the computer to guess it. Okay, so this game is actually inspired by Alan Turing. It's inspired by code breaking. And so you basically the way you play that game is one person is gonna come up with a particular color pattern where ordering is important, and then the other person will try to make a guess. Okay, I'm gonna guess your pattern is blah 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 blah, and the idea is you want to do it within a very small number of steps. Okay. And the way you do it, is the way the game is played is, once you present your guess, the person who is hiding the pattern will give you a clue. So if I remember correctly, a black peg as a score means you have one of these things having the right color at the right position. And then of all the ones that are not at the right position, the right color at the right position, if one is matching a color, then you give the person, a score of quote unquote a white peg, and so on. So you do give the other person a clue as to, okay, how much of a particular guess matches the actual hidden pattern. And by using the process of elimination, the idea is you want to cut down to one single choice within the number of steps that are permitted, and there are ways to optimize this too. So this is a game. I know it's not totally related to what we are talking about, but it does relate to counting, because now you can basically figure out how many ways can we arrange these colors, which can also duplicate. I think there are 6 colors and 4 positions, so 6 raised to the power of 4 would be the total number of possible ways to arrange the colored pegs. The idea is you kind of want to keep track of the ones that are still possible, and then you want to kind of pare it down as quickly as possible. And there are ways to optimize what pattern you should try to guess next in order to get it down as quickly as possible. Yep, you can optimize it. Okay, and the simplest way to do this kind of optimization is really just do an exhaustive search and find out what pattern or what path of patterns would be the most efficient to cut down to the one choice. So for those of you who look at this and go like, I don't see how this relates to computer science or what I'm going to do or why I'm even in this class to begin with. Well, let's look at another one that might, suggest that, hey, maybe this stuff is actually useful. It is a wired WEP encryption, which most of you should not know about or nor use at this time. But if you look it up, okay, it's this is something that the initial Wi-Fi routers use for encryption. Okay, so encrypts the packets and whatnot. It's called WEP, and I think the most advanced form of this is 128-bit. Okay, the key is 128-bit. And then by today's standard, this is totally insecure. In other words, if you configure your Wi-Fi router using WEP, for encryption purposes, don't be surprised that somebody hack into your network in less than a day. Okay, and the way they do that is by elimination. Basically they look at all the possible keys, given 128 bits, and then they look at your traffic, and there are certain ways to look at your traffic and rule out encryption keys. And within a day, probably less, because all of you guys are watching Netflix and all kinds of high bandwidth stuff. It depends on traffic. If you are using your internet very sparsely, you just use it like, if you use your internet as if you have a 1200 bps modem, it might take a while to break even WEP because your traffic volume is just not there to to support the cracking. So that means if you rotate your encryption key every day and you're using your internet as if you're using a 1200 bps modem, you are 100%, almost 100% secure. It's just chance that somebody might actually crack your network. Your microwave can crack WEP. Maybe your Fitbit, right? Your Fitbit probably has more than enough processing power to do that. So, but this is why, okay? This is why it is important to be able to generate the outcomes, okay? Because you are removing items from the set of all the possible outcomes as you go, okay? So this is why there are times when we want to ask, okay, if I want to look at the actual set of all the possible outcomes, how would I generate that? All right, so now we are going to go back to the notes. And the first one, in section 6, this one looks at all the possible permutations. And then in section 7, this is the one that looks at all the possible combinations. Now they look different, okay, but they really work out of the same kind of mechanism, and the mechanism is recursive. And this is also partially why this class has a co-requisite of 430, because the way we look at things, okay, is really kind of important. The recursive way of looking at things turns out to be a very productive way of looking at things, because we look at the base case. So let's think about a base case for something that seems to be really complex, okay, and we just look at this and go like, okay, what is the base case? So first, a little bit of notation. So the notation says, in the case where the outcome set of each trial Ti is independent to other trials, the outcome set omega of an experiment of M trials is the Cartesian product. So this is the easy one where you do have replacement. So when you do not have replacement, or when you have a case where it is without replacement, then it gets a little bit more complex. So we'll use the notation of omega I of t to represent the outcome set of an experiment involving I trials, starting with t as the initial set of trial outcomes. So now we want to look at the base case. This is the base case here, right here. It is in the form of omega 0 of t is the set of an empty tuple, okay? And I did not make a mistake in terms of the notation, by the way. This is actually correct. So the question is, what is it representing? Tech, what is this? Okay? Well, first of all, omega blah blah, okay, is the set of outcomes, because right here it represents the outcome set. So that explains the curly braces here, because we are dealing with a set here. The next thing is, what is this 0? Okay, what is it representing? Well, we see this I here is I trials, right? So we are now having a very silly experiment that has no trials. Okay, here's a coin, and let's not flip it even once. Okay, let's flip it 0 times, and I'm gonna ask you, what is the set of my outcomes? You go like, nothing, right? Well, but nothing is an outcome. Okay, so we have an empty tuple here, which basically means, well, nothing came out of it. Okay, but that so-called nothing does count as one thing. So that means if you count the cardinality of omega blah of t, the cardinality of omega it here should be p of the cardinality of t comma I. Okay, I know I just said something and most of you are probably not parsing it, because I certainly would not be parsing it because I'm not an auditory person. When I hear people saying stuff like that, it just goes like, shh. Okay, nothing sticks. All right, so I'm going to type it out. So what I'm saying here is the cardinality of using that omega as a function. So this time omega is a function. It is not a variable of t. All right, so this is what I want to figure out. What is the cardinality of this thing here? So this cardinality should turn out to be the permutation of bar t bar, which is the number of elements of the initial set of outcomes for the first trial of the entire experiment, and then I is basically the number of trials that we want to have in the experiment. So this should hold up. Okay, however I define the function of omega, however algorithm I use to generate the set of all the possible outcomes of an experiment involving I trials, when the first trial has t choices to choose from and it is without replacement, these two should match. Do we have any questions about this part here? And if you plug in a 0 for permutation, so you're basically trying to figure out the number of permutations given that you can choose from, n, which can be like a big, huge number of things, but you decide and say, let's just have 0 experiment. That value turns out to be 1. It's not 0. In other words, okay, so getting back to the birthday problems that we just talked about earlier in the class, right? So what if we have a class of 0? If we have a class of 0, how many ways can we arrange birth dates assigned to students? That's counted as 1. Okay, basically there's no one here, but it is still 1. The tuple has no items in it, but there's still an empty tuple as the only element in the set. All right, exactly. There's only one way to choose nothing. Okay, if I give you a bag of 26 items, okay, the alphabet of English, okay, and I say, but don't choose anything. How many ways can you choose nothing out of a bag of 26? The answer is 1. There's one way to choose nothing out of a bag of 26 items. So yeah, so you need to kind of ponder upon this sort of thing, because it really, really is important when it comes down to making sure everything is consistent. So because of that, okay, we can now have a base case. If you're thinking about recursion, this is how we stop that recursion, right? So the way we stop the recursion is when the number of trials left is 0. Then you can just come back and say, okay, there's only one way an experiment involving no trials can come out, which is nothing. Okay, but that nothing is itself a thing. Okay, it's a tuple of 0 items. It is an array of 0 items, and it is counted as one element within the set. So this is our base case. And I'm looking at the time. We only got 30 seconds to go, and I'm gonna go straight to the recursive definition here. You guys are going like, no. Okay, so this is the recursive case. If I give you T as the initial set of outcomes for a single trial, and I say I want to have I trials, what would be the set of all the possible outcomes? So this big U here is to say, okay, so let's assume that we choose E within this T as the outcome of the first trial of the entire experiment. Okay, so once you have chosen E can no longer be available to the next to the nested experiment. So this is the key of recursion. And I hope people who have signed out will eventually come back and listen to this again, because recursion is going to bite those people if they don't really understand how recursion is done. So in this case, the real key here is to look at an experiment with I trials and look at it as two things. Okay, we separate it into, the first trial is special because I actually get to see the outcome of the first trial. But once I have chosen something, the rest of the trials, I'm just going to look at that as an experiment with one fewer trial, and the first trial of that nested experiment is going to start with the same set that I started with, but without the one item that I have chosen as my own outcome as a trial. So that's the way of looking at recursion, is to break a larger problem into two parts usually. One part is easy to handle. Okay, this is my problem, this is my case. And then the rest of the problem, I don't want to solve that problem. I'm just going to give it to somebody else to solve that problem. But that problem turned out to have the same nature as the problem that I was solving. So now I can do a recursion, because now I know exactly which subroutine that can handle this case. It's the same subroutine that I'm in, except it is now having one fewer trial in this case, and the choices available to for the first trial of the nested experiment is going to be the same as what I start off with, but without the one that I have chosen for my trial, for the first trial of the experiment that I'm responsible for. So we are out of time, and obviously I really cannot get into this today. So we're going to continue the discussion on Wednesday, and then on Wednesday I'm going to give you an actual example. Okay, so I'm not going to give you an actual T to begin with, and I will start with omega 2 is fine, omega 3. Well, omega 2 is probably better, because otherwise it's really tedious to keep track of everything. So we'll have an omega 2, and then I'll give you an actual set of T. So this way we can do the recursion all the way down to the base cases like this one, and then back up again, and then we can figure out all of those intermediate pieces, and then finally get back to omega 2 of the actual set. So this way you have a visual representation of how recursion actually get things done, and why it is important in this case to define it in a recursive way. So that's going to be a preview. That's the preview of what we're going to talk about on Wednesday. And so right now I don't have anything else to talk about. So I guess I can get out of screen share and live stream. All right, see you guys all on Wednesday.